Welcome back. We'll start the second morning session with Akshay Krishnamurthy from Microsoft, talking about inference-time compute, scaling, and I guess making LLMs even better, as I assume what the goal will be.
Or trying to understand how they can possibly do this. Cool, thank you so much for the introduction and for sticking around. I know it's been a long 1 or 2 weeks. So I'm not a physicist. I'm a computer scientist, and it's very interesting to watch earlier talks because I know nothing about what's going on. It's quite fun. So this talk is just going to be about language models or generative models, and maybe trying to use learning theory tools, or trying to bring some conceptual clarity into some maybe mysterious things that they seem to be able to do, and specifically about self-improvement and test time scaling, or this concept you may have heard about. So this is going to be about language models. Maybe it's always good to make sure everyone has some idea of what a language model is. I imagine many of you have played with them, but maybe let me tell you a little bit about how they're trained. So there's usually 3 stages to training, or 3 stages to development of a language model. The first stage is pre-training, then there's this post-training thing, and then there's this inference-time compute. And pre-training is sort of in this extremely compute and data-heavy regime where you take all the text on the internet or something like this, and you run a very simple method, which is sort of read the first part of a sentence and train the model to predict the next token, and you just optimize this objective function using gradient descent on a massive corpus. And this sort of gets the model to learn syntax and various languages and so on and so forth. And then the second stage is post-training, which is somehow it operates in this sort of data scarce regime, and it's somehow, because of this, much more algorithmically diverse. And here you do all sorts of every company has a different post-training recipe. It's hard to know exactly what's going on. But they roughly try to get the model to maybe be better at following instructions, to do things that humans want, and not do the things that humans don't want, get them to be safe and not produce toxic content and so on and so forth. And then the last stage, actually, there's this inference-time compute stage. There's no data at all. There's just compute. So this is sort of using the model in sort of non-standard ways to get them to perform better than they would if you used them in a standard way. So you can do this by prompting them in some way. There's this thing called chain of thought prompting. You can add examples into prompts to get them to be better. This is called few-shot prompting. There's many other things you can do here. So these are sort of the 3 stages, and our group does work a little bit on pre-training, but I'm not going to talk about that today. I'm mostly going to talk about post-training and inference-time compute. And let's start with inference-time compute. So perhaps the most common way to do inference-time compute is this chain of thought prompting. Basically, you ask the model a question. You say, please show your work and think step by step, and then the model outputs 10,000 characters, or it outputs some long paragraph, and at the end it says the answer is 7. And somehow by doing this, the likelihood of the model producing the right answer is higher. So that's kind of cool, and it does work. But maybe it's a little bit hard to understand. There's another strategy that also kind of works, which is called parallel sampling. And here's sort of a cartoon of how parallel sampling works. You ask the model a question. Okay, this question is obviously very simple. But you ask the model maybe a hard math question. And then these language models are conditional distributions over responses given questions. So you can sample from these conditional distributions. You generate many samples. So maybe you generate many samples. It outputs different answers because it has some uncertainty or something. And then you sort of plug all these things into some kind of verifier and extract what is ideally the correct answer. This is this parallel sampling. Sometimes people call it parallel sampling. People call it best of n or something like this. And I guess I'll use both names interchangeably. And just to show you that this is a good idea, here's an experiment that we reproduced that originated, I think, from this large language monkeys paper out of Stanford. So here what I'm doing is I'm taking a bunch of different language models. I'm asking them math questions, kind of college-level math questions. And for each question, I'm saying, please show your work, and then produce the final answer. But then I ask the model to do this 32 times. And so when they do this, they show 32 different reasoning traces, and then 32 different final answers. And then I check if any one of these final answers is correct. So that will be the accuracy where n is 32. Okay, and what you can see is as you increase n, you generate more and more responses for the same question, and then you check if any one of them is correct. You significantly boost the model's performance. And you can do much, much better than the standard way to decode, which is this thing called greedy decoding. So greedy decoding is what's displayed in like the dashed lines. And this parallel sampling or best event sampling can do much, much better than this. So there is some value to spending this extra compute, generating many, many responses, and trying to find the right answers. And maybe just as like a tangent, basically this idea is what is used to train all of these reasoning models like O3 Mini, O1, Gemini, what is called flash thinking, whatever, all these things, Claude Sonnet. All of these, the main way that people train these is they first pre-train the model, then they do some other stuff, and then they run this parallel sampling, they find the correct answers, and then they like train on those further. So you interact with this verifier to get the model to be better at reasoning. Okay, but you know, like maybe there's a lot of applications where you might not have access to the ground truth verifier, and so a natural question is, what can you do if you don't have access? And maybe somehow one idea that you might think of is, well, like my model can like read its own responses, so maybe I can use the model as the verifier. So maybe the picture you should have in your head is like this. I have a question, I ask my language model to produce many answers, and then I ask my language model itself to score or grade or evaluate whether these answers are good or bad, and somehow from what the language model produces in this like verification stage, I select one. This is maybe called self-verification. And if you can do this somehow, it raises the idea that maybe you're kind of actually like self-improving the model. You take the model, it's just used in a non-standard way, and somehow you've made its performance better. So this is like, I improve the model's performance just by using the model itself in some non-standard way, self-improvement. And I think this is kind of a fascinating phenomena. Like when we started working on this project, there were some empirical demonstrations that this is possible, but very little understanding as to why. And every time someone wrote one of these self-improvement papers, like there would be this discourse about whether this is like violating the data processing inequality. So the data processing inequality is just saying that when you take some, you learn some distribution and you like post-processed it, you can't produce more information, right? So this is sort of like, I'm just doing post-processing. There's no like access to new information at all here. So somehow you shouldn't be able to produce more information. Maybe like, why can you improve the performance of the model? And what we like realized, I guess, is that like, this is not only an information theoretic situation, there's also like computational considerations. So what's happening here is like you're using compute to extract information that's in the model already. So maybe, okay, like a cartoon that I like to tell people about is, what's going on here is like, I give the language model a test, or there's a set of questions, I say, hey, please solve these questions as a pre-test, and then go lock yourself in some dark room with no access to any textbooks or internet or whatever, hang out there for 2 hours, come back, solve the tests again. The post-test performance is much, much better than the pre-test, but like no information. The model could just, I don't know, think for itself or whatever, right? There's no information was obtained. Okay, so this is sort of our speculation as to why self-improvement is possible. It's some computational phenomena. We'd like to go a little bit deeper and try to understand what is the mechanism behind self-improvement. So like how could it possibly work? And for this, we propose this idea called sharpening. This is in a paper we published at ICLR. Okay, it came out in archive last year, but it was presented at ICLR this year. It's with like Audrey Huang, Adam Block, Dylan Foster, who spoke here earlier, Dhruv Rohatgi, Cyril Zhang, Max Simchowitz, Jordan Ash, and myself. And sharpening has these two parts. There's like a hypothesis and a mechanism. The hypothesis is that like the language model as a verifier correlates with the downstream performance of the task you're interested in, or maybe the verifier correlates more strongly with downstream performance than using the language model as a generator itself. And maybe this is possible because the model is like better at verification than generation. This is something that we see a lot in computational complexity theory, like verifying that your solution to the traveling salesman problem is correct is much easier than actually producing the solution to the traveling salesman problem. And then there's also this sort of, hypothesis that's been floating around the deep learning community that these models have hidden knowledge that's hard to extract. So these are sort of some speculative reasons as to why a model might be better at verification than generation. But let's posit that it is. And so if the model's better at verification than generation, maybe what you want to do is actually use the language model as a verifier to improve the language model as a generator. You want to like tilt the language model as a generator towards producing better responses. And you can do this maybe by training. So the picture to have in your head is something like this. language model as generator produces responses. It's some distribution that I'm displaying in some cartoon histogram here. And the language model as a verifier assigns some kind of score or reward to every response. So this is like the reward function, this orange line. And what you'd like to do is use this information to move the distribution of the language model as a generator to move towards the mode of the reward and also maybe like concentrate. And this concentration is what we call sharpening, or why we called it sharpening. Okay, so in the next couple of minutes, what I want to do is two things. One is I want to validate that this hypothesis seems to be true in practice. And for this, I'll use inference-time compute, parallel sampling, best event sampling. And then I want to tell you about some training schemes that you can use to amortize the computation of parallel sampling into the generator directly to sort of self-improve the model. Okay, before that, we need to introduce a little bit of formality. Okay, language models are very complex. It's too hard for me to reason about them. I like to try to abstract things away. So I'm going to just say a language model is a distribution. It's like a conditional distribution over responses y given prompts x. It's like all you have to know. You don't need to know what a transformer is. You don't need to know what self-attention is. That's it. And the self-reward is some way of using the language model to assign scalar rewards to prompt response pairs. So it's just some scalar valued function. And maybe some ways you can do this is, the language model is a distribution. You can like associate the probability of responses as the reward, like sequence level probability or log probability. Turns out this is maybe not the best idea because very long responses tend to have very, very small probability. And so you might want to do something like length normalize. And then there's sort of more sophisticated things you can do. You can maybe try to do majority voting or prompting a language model to score its own response and some stuff like this. So the choice of self-reward is going to be like a design decision that I don't know how to, this is not up to me to decide. But once you have committed to one of these, a natural idea is you say, okay, I'm going to use the language model. I want to like basically find responses that maximize self-reward. So use the language model as a verifier to tilt the generator towards these things that have high reward. Okay, make sense? Okay, so now let's turn to this validation of this hypothesis. So this is sharpening. Okay, the way I'm going to validate is I'm going to use this best event algorithm. Let me just tell you precisely what it is. It's very simple. I sample n. I have a question, prompt x. I sample n responses from my conditional distribution. I get y1 to yn. I just return the one that has the highest self-reward. Okay, that's it. There's a typo here, but okay. And this actually works pretty well. So here I'm showing I took 7 language models on 6 kind of like reasoning data sets. And I'm generating 50 responses per question. And I'm choosing the response with the highest log probability according to the model itself. That's like the best of n strategy. The other strategy is I just generate one response using like greedy decoding, this very, very standard like default decoding method, default generation method from all these models. And I'm plotting like the percent improvement of this best of n thing over greedy on the downstream task performance. Like, did you get the math questions correct? And okay, you don't see like uniform, the improvements are not uniform, but basically for every model and every task, there's some model, every row and every column of this matrix has some non-trivial win. And remember, I told you this log probability is kind of maybe the worst possible reward function you could do. If you normalize by length, this matrix, all the color turns more blue. That's great. And then if you use majority voting, the performance is much, much better. So this is just to say that it does look like actually using the model, like some internal way the model can be used to score its own responses, actually does give you quite a lot of lift. Okay, so that's validation. Model is quite good as a verifier. Okay, so now let's turn to amortizing. This is like I want to train the model by interacting with itself as a verifier to become better just directly. Okay, so here, again, a language model is just a conditional distribution over responses y given prompts x. And let's just focus on this log probability as the self-reward function. And I'm going to assume that prompts are sampled from some distribution mu. And to think about designing algorithms here, I'm going to we're gonna like write down like a mathematical framework. And so the concrete objective is this pack learning style thing. So I want to find a model pi hat, and I say such a model is epsilon delta sharpened if for most prompts, most of the mass of my sharpened model is on the log probability maximizer, on the maximally self-rewarding thing. Make sense? Good. So this is like if you know about statistical learning theory, this is like very close to pack learning, except this is actually not a statistical problem at all. This is like purely a computational problem because you can just do computation with your base model to find the maximum likelihood response. But what I want here is that when you do like standard decoding with pi hat, you don't waste a lot of inference time effort with pi hat. You can basically produce these nearly maximum likelihood responses very, very quickly. Okay, so this is actually just a computational problem. And maybe the first thing to ask is like, what is the computational complexity of this thing? And okay, unfortunately, this is NP hard, even for probably the most simple policy class you can imagine, which is like autoregressive softmax linear policies. So this is something that we proved in our paper, but generally I view these things as like reasons to try to capture more structure in your problem. So this result I viewed as like maybe overly pessimistic because maybe the real world is not like so worst case, and this result only applies to linear policies, which I don't know, nobody really cares about them because we use these massively deep networks. So towards trying to do something towards going beyond this, I'm going to introduce two wrinkles to the problem. So one is, how do we go beyond linear policies? And this is, we introduce like an oracle framework, which essentially converts this computational problem into a statistical problem. So we do this by saying you actually don't have access to the base model directly, but instead you can only like sample and query various things, and we're going to measure your compute by how many samples did you make. So the protocol is you can sample n prompts. For each prompt, you can sample capital N responses, and you can query the self-reward on these capital N responses, or capital N times little n responses. And the sample complexity is the product of these two. And I'm going to use this as a surrogate for computational complexity. So now somehow I'm only going to talk about sample complexity. And an algorithm that has good sample complexity, we're going to map that onto saying an algorithm will be computationally more efficient in practice. But this is great because somehow statistics is somehow more powerful than, I don't know, computation. Or it's much easier to reason about in a statistical way than it is to reason in a computational way. Okay, the second thing is we're going to try to go beyond the worst case by introducing an instance-dependent notion of difficulty of the problem, and this is through a parameter called coverage. So the coverage coefficient is just like 1 over the probability that the base model plays the optimal action, the optimal response, on average over the prompts. And this thing sort of measures, like, it really does measure how easy the problem is. I mean, in fact, it just like governs the performance of best event. If this number is small, then best event will just have very good performance because with very few samples, you will find the maximally self-rewarding thing. And in practice, this number, okay, in the worst case, this number can be as big as like the response space for sequence level log probability as the reward function. But in practice, it turns out to be, it seems like it's much, much smaller. In fact, this is basically what this plot is showing you. With very, very few samples, you can actually start getting all the things correct. Right? This is a sense that the model actually just does have reason. It could be the case that you need exponentially many samples because these response spaces are very, very large. It could be the case that you need exponentially many samples to find the correct answers just by sampling, but it turns out you don't. You need 32 or something. So this is the other wrinkle. Okay, so that's sort of the framework, and actually that's the main thing I want to communicate to you about this. I will tell you a little bit about theoretical results, but I think the part that's cool about this is both like conceptually that like self-improvement is possible and that you can actually do math to reason about it, not the specific math that we did. So the framework is this, you have this like definition of sharpening, this like pack learning style definition, and then you have these two wrinkles. You have this oracle framework where you convert a computational problem into a statistical problem to help you do math, and then you have this coverage parameter to go beyond the worst case. And okay, so we did a bunch of theory. I will just tell you very, very little about it and then show you some experiments. The first thing is that there's some lower bound that says actually coverage is an essential instance-dependent parameter. So you do need like coverage over epsilon squared samples to sharpen. The second thing is an algorithm that's super simple, that's just based on supervised fine-tuning, that actually gets the optimal sample complexity. So it's minimax optimal, very, very simple. And it has a kind of interesting representational condition. So this algorithm is going to be based on just trying to amortize the computation that best of n does. But best of n sort of uses your model in a non-standard way. And if you're going to try to distill that back into your model itself, you might need your model to have more parameters. Like best of n is kind of like shooting out 50 trajectories, and you might need a much wider network to do that internally to the model itself. So there's some, you might need to use more parameters to actually try to amortize the computation of best of n. That's SFT sharpening. RL sharpening, there's some algorithms that are not really based on supervised learning, but based on reinforcement learning. You can study, you can analyze these things. There's some like kind of standard ones that people tend to use in practice, but you can actually do some kind of non-standard things that you use the policy to explore. And by doing so, you can actually go beyond sort of this lower bound. To do this, you actually have to operate in some sort of like deviation from the sample and evaluate framework, but you can do this. So somehow exploration can buy you something here as well. Okay, that's all I really want to tell you about the theory. You can check out the paper for more. I will show you some experiments and then some things that I find puzzling. Okay, so this is SFT sharpening. So we're just going to try to amortize best of n sampling. So we take a policy. We have a data set of questions. For each question, we use the one, like the initial model, the reference model, to shoot out 50 trajectories, 50 responses. And we take the response that has the highest log probability according to the model. And now we have a data set of prompt and single response pair, the response selected by best of n sampling. And we supervise fine-tune on this data set. Okay? That's the algorithm. This algorithm does something non-trivial. So what I'm showing you is over the course of supervised fine-tuning on this data set, your SFT policy does something, it actually does better than greedy decoding, which is the black dashed line, with the original model. But it does not reach the skyline performance of actually running the inference-time compute strategy on the test set directly. And this might be because of this representational condition. I'm using the same number of parameter policy to try to amortize this best of n computation, and maybe I don't have the capacity to do so. And we also actually improve the log probability significantly over greedy decoding. Okay, so this is just, you can amortize this computation. Okay, maybe just to be clear, for this blue line, I am just doing greedy decoding with the trained model. So the model was trained to amortize best of n, but then I just use it in the standard way. And you can do something non-trivial here. Okay, for RL sharpening, let me tell you sort of like a proof of concept experiment that's, we're trying to like flesh this out a little bit in a joint project with Jens Toils. So this is like, this is not actually training a model. This is, okay, how do I explain? We have developed some way to do exploration with language models. It can actually be used in several ways, but one way is actually to filter a huge corpus into a very small set of diverse responses. And this, the experiment here is showing you that this is actually a good idea. So what we do is we have some data sets of reasoning questions. For each question, we generate like 10,000 responses from an original model. And then we're going to filter this down to like 100 or 200 responses. We're going to try to very, very aggressively filter this in two ways. One is we filter using this exploration strategy. And the other way is to filter just by randomly subsampling. And what we want to know is like, how aggressively can I filter while ensuring I actually keep the correct answer? So how many samples do I need using these filtering strategies to get the right answer in my subset? And what I'm showing you here is that for many of these model task pairs, the exploratory method can actually subsample like to a factor of 2 to 5x smaller than random sampling. And this is sort of showing you that if you were to explore, you have a much higher chance of actually hitting the right answers. And if you map this onto coverage, it's like I improved coverage by a factor of 2 to 5, which should translate to improvements in sample complexity and sharpening, which should translate to improvements in computational complexity when you actually run these things in practice. So that's the validation experiment. We're actually, I mean, Jens is actually just incorporating this into a reinforcement learning training loop to see if we can actually get significant improvements end to end. Cool. Okay. Let me tell you something I find extremely curious about this, that, like, in my opinion, fascinating open problem, and this is about going beyond amortizing. So our hypothesis for what is going on in self-improvement is your amortizing computation that you could have just done at test time. And, like, that seems extremely believable to me, but then after we published this paper, we started seeing these experiments where people are somehow going beyond this. Let me show you just one of these. Okay, so this is an experiment where they do reinforcement learning training to try to amortize the computation of majority voting. And if you believe this amortization hypothesis, you would expect that the blue line, which is like after amortization, matches the dark gray line, which is using majority voting with the original policy. But the blue line is actually always better. So somehow they've done something beyond just like cloning what you could have done at test time. So somehow you can actually improve over inference time sharpening. And this is actually not captured by our theory at all. But it seems there's actually quite a few experiments that show you can do this. And it's not clear to me how, when, why. It's very mysterious. And this is actually related to what happens when you actually have the true verifier as well. So it seems like roughly the same thing can happen when you use the ground truth verifier. So this is what everybody does to train these latest reasoning models. And there's been this big debate about whether these models can do something more than sharpening or not. And so this experiment is sort of showing that if you do like standard reinforcement learning training using the ground truth verifier, you cannot do anything better than sharpen. So what's happening here is that the blue line is the coverage curve, or the the coverage curve or the pass-at-end curve for the original model, and the red line is the pass-at-end curve of the RL trains model. And what you'd hope is maybe the red line is actually just has a higher peak than the blue line. That means it actually can solve questions that the original model cannot solve at all, like even if you increase the compute of the original model. But what this paper shows that like you can't really do that with the standard RL recipe. But then there's these other experiments that show like maybe you can if you use a non-standard RL recipe. So here the blue line is the original RL model, the original model, and the green and orange lines are like checkpoints of their RL training, and somehow you're doing much, much better than what the original model can do. The original model cannot do anything at all on this task, and now you can actually get like 100% accuracy. So this seems to be also like going well beyond the sharpening regime. And I forgot to mention, okay, like one view is that this reinforcement learning with the verifier is just sharpening at the outcome level. You don't care about what the reasoning trace is, but you just want to, take the final answers that you can produce with lots of compute and do them directly. But again, similar to the previous slide, it's just not clear at all to me, like why you can go beyond amortization. What's a good like framework to reason about this, and how do we design algorithms that do it reliably? Somehow, obviously, this is what we want, right? Like, you pre-train your model, you'd like to discover new capabilities that your model couldn't do at all. And it's not clear how one can do this. Okay, let me tell you very quickly about like something else, which is some like mystery we found that we kind of answered. Okay, so we were running these experiments about like, best of n with some self-reward function, and one of these experiments I ran, I found very curious. So what I'm showing you here is I'm doing best of n sampling with log probability as the reward, and I'm plotting the downstream accuracy. And in the first part of the talk, I showed you that if you increase the number of samples, you should be improving the downstream accuracy performance, and that's kind of true to a point. But once you scale the number of samples too high, you actually start degrading the downstream performance. Like you get this sort of like hill, right? Like performance goes up on the downstream task, but then it like drops and maybe plummets disastrously. And we actually found that this happens in many situations. So there's another way people use these language models is they have a learned reward function that's not your own model. And you can do best of n using the learned reward, and the same thing, exactly the same thing happens. And we also found some experiments in reinforcement learning. When you do reinforcement learning training with the self-reward function, your performance can shoot up and then degrade, like just plummet. So maybe one way to interpret this is actually like you're not guaranteed monotonic improvement with increasing compute. And this is sort of violating all these scaling law things that is like actually powering the whole industry. So we really do want like a scaling. We want compute monotonicity. And you don't just get it for free with inference-time compute. So we have some framework to think about this, and this involves using true reward functions and learned reward functions. Again, a language model is just a distribution over responses given a prompt. Now we want to find like the highest true rewarding response, or a policy that produces responses that have high true reward. But we don't know the true reward function. Instead, we know some learned reward that is close to the true reward in some like least square sense. And this is just a computational problem again. We're going to do the same thing, convert it to a statistical problem using some sample and evaluate framework. And in this framework, just the framework is you sample n responses from your base model. You can query for the learned reward, and then you have to return some sample that you have. And this is something we did in this work with Audrey, Adam, Qinghua Liu, Nan Jiang, and Dylan. And so in this framework, you can analyze best of n, and you can show that if you tune n optimally, you get some rate that depends on coverage and the error of your learned reward model to this 1/3 power. This is actually if you have the optimal n. If you just write down the error guarantee, you'll see that best of n is non-monotone with n. And this is exactly what we see in practice. You increase n too far, and then the performance degrades. And to fix this, maybe the issue for why this happens is, like, as you increase n, you get closer and closer to the maximizer of the learned reward. But the maximizer of the learned reward is not necessarily the maximizer of the true reward. And under the squared error guarantee, you're moving more and more into the tail, where the guarantee is sort of degrading. So you run into this risk of overfitting. And once you realize this, maybe the answer to solve this problem is to do regularization. This is exactly what we did. It turns out the right regularizer is to use this chi-squared divergence. So you want to sample from this regularized policy, where you optimize the learned reward, but you try not to deviate too far from the base model. So your regression, your learned reward guarantee is still valid. And this thing can be solved in basically closed form. You get some very nice form that you can actually just do rejection sampling from. This gives us an algorithm that we call inference-time pessimism. The name comes from offline reinforcement learning, but maybe it doesn't matter too much. And the guarantee is that if you tune this regularizer correctly, you can get somehow a similar shaped guarantee, but the power is actually better. But maybe the more important thing is actually this thing is actually monotone. So you can, if you tune, for any fixed beta, if you scale n arbitrarily, you will not degrade the performance. And this gives you like the scaling law that you like. And we actually see this in experiments. So the solid lines are inference-time pessimism. As you increase n, the performance does not degrade. The dashed lines are best of n for various language models. And as you increase n, the performance does degrade. OK, let me basically end there. So maybe to summarize, reinforcement learning is actually widely used in language model pipelines to amortize interaction with a verifier. The verifier can be like the ground truth. This is what's powering the O series or DeepSeek and whatever. It can be some learned function that you downloaded from Hugging Face, or it can actually just be yourself. That's kind of cool. I think there's tons of mysteries. There's very little consensus on what algorithms you should be using. There's very little understanding of what's going on. And maybe as an advertisement, similar to Liang, we're organizing a workshop at NeurIPS about reasoning in language models. So if you're interested in this stuff or you're working on it, please submit your work, and we'd be happy to see you there. Thanks.
All right, thank you. Questions? This one up here. Let me get up there. Can you pass this down
Hi, thanks for the nice talk. I'll actually later give a talk where we tried some of these techniques on a physics data set, so best of n and model self-verification and so on, so that will be interesting to compare. So I think one comment or question I have is that I think that when you, for the difference between amortizing the effort of best of n during inference or in training time, I think one thing that matters there is that problems are dependent on each other. So if you get good at one problem, you will get good at other problems also. And also problems are sort of compositional, especially like hard problems. So if you get good at solving simple problems, then afterwards you need to sample less problems to make hard problems, right? And to
Yes.
solve a hard problem.
Yes.
And therefore, I think for these reasons, these two things shouldn't match, right? So I think it's
Yes.
better to do this during training. You probably have some theoretical insights into that, but yeah.
I totally agree. So my theory, which I'm trying to get people to help me work on, is like the reason you can do better is due to curriculum, which is roughly what you're saying, right? There's some easy questions, and you train on those, and you actually like start improving coverage mysteriously, I guess, on hard questions, right? I think that's correct. Actually, one thing I didn't tell you for like this plot, they didn't do RL on only this task. They did RL on like 300 tasks, and some of them, their original model actually does something non-trivial. So because they're like bootstrapping off of the non-trivial performance on task 1 to get good performance on task 2. I totally agree. I think one thing that'd be really cool is to show that somehow if you don't have a good curriculum, you can only sharpen.
Okay.
Right, so that's like the only way you can, get this behavior is through curriculum. Right. I think that'd be kind of cool.
Okay, yeah,
And-
I would
and
love
maybe
to
one
chat
more comment
about
on
this
this.
a bit more later.
It's not clear to me how to define a curriculum. I think the intuition is very natural, but what's like a good formalism of this, right?
Okay, thank you.
All right. Were there other questions?
Yeah, so since we're still on this slide, looks like in the low N area for all of these figures, there is a boost, right, from using RL. So is it correct to think like RL can get us a good answer faster, but maybe not necessarily discover better answers? And is that too pessimistic?
That's the amortization view. The amortization view would be shift this curve to the left, but not increase the peak.
Okay.
Right.
But in general, it also seems to shift the peak down too, right? As
It
you were
also
saying.
seems to shift the peak down. Yeah. So maybe another comment about yours, like these plots suggest some negative transfer, like negative curriculum. You improved your performance on some questions, but you actually degraded the performance on others. So when do you get positive transfer? When do you get negative transfer? I think is very mysterious to me. Quantifying these behaviors, I do think somehow, okay, improving the left side of the plot is great, but degrading the right side of the plot is quite bad. So why can we not, maybe we should at least take the pointwise maximizer of these two lines. That'd be reasonable. Somehow we can't do that, right? And then you'd really like this, right?
Maybe another
know how
question,
to
if
do
it's
that.
okay. Is you briefly mentioned using exploration to some extent to filter the data set, right? So can you say a little bit more about what that means? And or do I have to wait for a paper
You
to
might
drop?
have to. Well, I don't know how much I should. But I mean, you can imagine like using like some sort of novelty bonus. So you like imagine collecting responses in sequence, and you can penalize similarity to the response you've already seen. So we just have some
Standard RL exploration. You'd say like standard RL exploration techniques.
Yeah. In fact, that's how we.
Okay.
That's how I got Jens to do this project. Let's like just ablate what RL exploration works in language models. So yeah, you could imagine if you know like random network distillation, you can imagine doing that, right? Something like this. Yeah.
Thanks.
Yeah. So in this experiment, we're using those things in a non-standard way, but the experiments Jens is running now is like basically the standard way. We're using these for like core set computation, like throwing away 90% of the data. But you can also just do it like, use an exploration bonus in your RL loop.
Has anyone tried to play these type of games with multiple LLM agents? I'm just thinking along the lines of like one student in a room by themselves can do some problems. Other student in a room by themselves can do some problems, but the combination of two students in a room can often do more problems than the sum of the two.
Yeah.
And I wonder if there's any like utility in having some multiple LLM agents kind of trying to back and forth say, I think you're wrong for this reason, or I think you're wrong, and then somehow see if they coherently add up to more than the sum of their parts.
Good question. I haven't seen this exact thing, but I have seen okay, this is a bit bizarre, but you can actually prompt a language model. You say, like, here's some math problem. Please solve it like you're Isaac Newton. Or please solve it like you're Gauss. And the generations are very different. So you basically have them take on different personas.
Right.
And then that's like some form of exploration. You're getting diversity in response. Like if you take two students, they're not allowed to talk to each other, but they do solve the questions. And you look at the union of their solutions, maybe you actually get better, total accuracy or something. This is something like that, right? So I think that is doable. Like people have done it. It kind of works. Getting them to interact, I think, I haven't seen this too much, yeah. But it seems very natural.
Yeah, I mean, who knows? Maybe it'll work. There was one over there.
Yeah, so I think part of what I'm wondering is you give a set of questions on which the network creates responses and refines based on that. Is there like an art or a way to pick those questions? Like is there any guidance on what questions would be good? And maybe could the network even itself ask questions that maybe it can think, like going to the meta level, right?
Yeah.
Have the network generate those.
That's like what I want our group to do next. What is this definition of curriculum so that you can get this positive transfer, and then can you generate this curriculum yourself? That's exactly what I want to do. I don't think there's a good understanding of this at all. People are trying, the field moves very fast. So there are papers about this, but I think they're kind of limited in scope and very bespoke heuristic methods. What is a clean method for doing this? It's not so clear. But I think this is a great question. Yeah.
All right. Any other questions? If not, let's thank our speaker.